Hello, this is Physics Chapter 1, Lecture 1. For this lesson, you'll need your Chapter 1 lecture notes. You might want a highlighter and your physics textbook. And the first problem that we're going to work is on page 8. All right, so with Chapter 1, we're just starting with the most basics of motion. So, kinematics is motion in one dimension. So that's motion that's just up and down, so the y-axis, or motion that is left and right, the x-axis. That's all kinematics is. If you're going to the right or up, that's the positive direction. So your answer will be positive. If you're going left or down, that's the negative direction. So the negative just means left or down. It doesn't mean that you have a negative speed or a negative distance. All right, so the next thing on the notes, displacement is the change in an object's position no matter the path taken. So it's the shortest distance from point A to point B. It's different than distance. Displacement and distance are different. Displacement is a vector quantity. That means it contains directional information. All right, so let's get a little more into that. What's a vector quantity? So in the book, vector quantities are bolded. All right. And it'll have directional information, and that direction can be denoted by a mathematical sign, plus or minus. That's what we'll be using when we're dealing with kinematics. It can be a geographical direction, such as north, south, east, or west. We'll do that a little bit. It can be at an angle, so once we get to Chapter 3, we'll start using angles and trigonometry, and so we'll have an angle to tell the direction. Or it could just say left, right, up, down, something like that. And there's many other ways that you could to list a direction. A scalar quantity is measurement with no directional information. So time, speed, distance, those are scalar quantities, and they don't give any kind of directional information. They don't say north, south, east, or west, etc. So the first problem that we want to work is on your own 1.1, and this is on page 8. All right, so just follow along with me in the book. Hopefully you can see this. If not, you can just follow as I read it. It says an ant starts at his anthill, walks 15.2 centimeters to a crust of bread. He takes the bread, turns around, walks back towards his anthill. He stops after he's traveled 3.8 centimeters and eats part of the crust of bread. What's the total distance he has traveled up to that point, and what's the total displacement? All right, so distance and displacement, two different things. They can be two different numbers, and they can be the same. It depends. All right, so let's draw this out. The ant walks, so we've got an ant. I'll do some terrible art here. All right, I know they have a lot more legs than that. And he walks to a crust of bread, so I'll have this miraculously standing on its end. So the ant walks 15.2 centimeters to the crust of bread. And then stops, takes the bread, turns around, and walks back towards the anthill. 3.8 centimeters. And stops. All right, so the distance that the ant traveled is the sum of both numbers. So distance, we'll use D. Distance is 15.2 centimeters plus 3.8 centimeters. Right, so the total distance is 19 centimeters. But displacement is different. Now, in the book, displacement is uses X, okay, and it's bolded. But we can't really bold when we write. So what we're going to do, and in fact, we're going to do delta X because it's change in displacement. We put a little half arrow over it to signify that it is a vector. So displacement is the shortest distance from point A to point B. In this case, we could call this point A and this point B. Okay, so it's just the distance from A to B. So displacement is going to be 15.2 centimeters minus 3.8 centimeters. And that's 11.4 centimeters. So displacement in this particular case is different than distance. All right. So there's your first physics problem worked. Hope you think that's not too bad. All right. The next concept is velocity. All right? Velocity is the time rate of change in position. Velocity is a vector quantity. So you've got some space here. The velocity equation. All right, and I'll go ahead and erase here. So you're going to see this equation a lot. Velocity is the change in displacement, not distance, change in displacement over the change in time. Okay, so that is an equation you absolutely have to memorize. So I'll put an asterisk by it. And similar to velocity is speed. Now speed, not a vector quantity, so we don't put a half arrow over it. It's the change of distance traveled. The speed equation is the change in distance over the change in time. So speed and velocity can be different. Speed will use little s, so change in distance over change in time. And again, not a vector. So let me give you an example of, so you've got some space at the bottom of page 1 of your notes. I want to give you an example of how velocity and speed can be vastly different. And what I'm going to draw out is the basic path of the St. Jude's Marathon in Memphis, Tennessee. So this is a marathon that I've run a couple of times. And a marathon's 26.2 miles. And so the path, let's say our start is right here. And you don't have to draw it on your paper exactly like this, but you can do it roughly like this. So you start out like this, and we come around like this in kind of a big loop. All right, and it goes like this, and at this point you've hit the halfway point, or the half marathon, 13.1 miles. And the half marathon people get to kind of pull off and go and finish their race, but the marathon people have to basically kind of turn around and go back the other way. All right, and they end up something like right here. Okay, so the start here and the finish is actually in a baseball stadium, which is kind of cool, is right there. The distance between those two spots, or displacement in this case, between the start and the finish, displacement is roughly, we're going to say it's 1 mile. But the distance run is 26.2 miles. So velocity is going to be the change in displacement over the change in time, which is 1 mile over, and let's say it took 4 hours. That's roughly, I think I ran my first one in 3 hours and 50 minutes, but we'll go with 4 hours. So 1 mile over 4 hours. That's going to be 0.25 miles per hour. All right, that's our vector information, and it's roughly south, the way I drew it there. Okay, the speed, though, is different. That would be 26.2 miles, the total distance run, over 4 hours. And that's about 6.55 miles per hour, which looks a lot better, and it doesn't have a directional information. So that looks a lot better than the 0.25 miles an hour, right? So my velocity was crummy because it wasn't a straight line race, okay? But my speed, which is what we really care about in this case, was about 6.5 miles an hour. Okay, that's just an example to show you how different velocity and speed can be. So I'm going to leave these two equations up, and we'll get into a couple of math problems that deal with velocity and speed. So on your paper, let's look at on your own 1.2. So in the book, flip over to page 12. Okay, so we'll read through this. 1.2 says a mail carrier drives down a street delivering mail. She travels 3 times 10 to the second meters down the street. Of course, scientific notation, that's 300 meters down the street in 332 seconds. She then turns around, heads back up the street, but because of the way the mailboxes are placed, she only needs to travel 208 meters in that direction. And that trip takes her only 230 seconds. So 2.3 times 10 squared would be 230 seconds. What was her velocity as she traveled down the street? What was the velocity up the street? And what was her velocity for the entire trip? So let's draw this out. So we're on your own. I'll quit writing OYO. We'll just go 1.2 on page 12. Draw it out. She's going down the street. And let's say that down the street is the positive direction. Okay, so down the street, it's 300 meters. And it takes 332 seconds. Then the male person goes up the street, and she travels 208 meters, and that took 230 seconds. That portion of the trip. So down the street is positive, then up the street is the negative direction. So these are directions. Okay, so it asks, what is the velocity down the street? So it's the change in displacement over the change in time. Right? That's going to be 300 meters over 332 seconds, which is 0.904 meters per second. And then the velocity up the street, also change in displacement. We won't have to write this every time, over change in time. Now here's where we have a little bit of a new concept that we have to look at. The direction is negative, so we have to put negative 208 meters over 230 seconds. I wish the author had given a different number here, but that'd be negative 0.904 meters per second. So that's the velocity down, the velocity up. Now the velocity for the whole trip, remember, is the shortest distance from start to finish. So if we call this A, we call this B, the displacement for the whole trip is going to be 300 minus 208. So that's 92 meters. So the velocity of the whole trip is going to be 92 meters over, and you have to do the whole time, 332 plus 230 seconds. All right, so that's going to be 0.16 meters per second. It will be positive because the male person ended up to the right, or ended up down the street. Okay, so 0.16 meters per second is what I have. Let me double check that. So you're also going to want a calculator. Yeah, 0.16 meters per second. So our three answers are right there. Okay, important. Even though the math is easy, very important concepts. Okay, so pause the video if you need to, and we'll go on to the next problem. Looks like I need to get a wet rag in here for the erasing on this. I'll have that for the next video. Sorry about how much time this is taking. Please fast forward. All right. So on down your notes, we're going to go ahead and do on your own 1.3 on page 13. So reading through that, it says a boat travels straight down a river at a speed of 15 meters a second. If the boat travels a distance of 34.1 kilometers, how long was the boat ride? Okay, we did a lot of, in this particular case, of course, we have a speed is 15 meters a second. And the distance is 34.1 kilometers. So you can see our units are different. We have meters and kilometers. We're going to need to change one or the other. I'm going to go ahead and change kilometers to meters. So we won't do this every time, but if you have from your chemistry, you can remember 34.1 kilometers. Put that over 1. We're going to change that to meters, so we put meters on top, kilometers on the bottom. The 1 goes by the bigger one. There's 1,000 meters in a kilometer, so that'd be 34,100 meters. You don't have to show me this work, but if you need to do that work because, you know, it's been a while since you've done it, feel free to do it this way. All right, so we've got 34,100 meters. We want to know how long was the boat ride. So what is the change in time? Okay, so if we have speed, do a lot of algebra in physics. Speed is equal to distance over time. Then we know solving for time, that's going to be, we're going to flip these two. Time is distance over speed. So time is going to be 34,100 meters over 15 meters per second. So how long did it take? It took 2,273 seconds. All right, beautiful. Okay, pause video if you need to, and we'll keep on moving through the notes. Okay, so let's go with a few more terms here. Instantaneous velocity is velocity at a single moment in time. We do not do this in algebra-based physics. Instantaneous velocity can be calculated with calculus. All right, so if you ever take calculus-based physics, then you will go through that, or if you ever take calculus. Average velocity is what we'll be doing in this class, okay? Velocity over a period of time. So if you'll look in your note, in your book on page 16, you'll see the position versus time graph. And going through these, so and we'll look at, I'll go ahead and open your book to this position versus time graph here. So the slope is the velocity. Okay, so you can see the slope is positive here, the slope is negative here, so velocity is positive here and negative here. The velocity is constant anywhere the line is straight. So you can see on this particular graph, the velocity is constant kind of between 0 and 2 seconds because you kind of have a straight line there. And pretty constant here between, say, 7 and 10 seconds. But where it's kind of bumpy and curvy, then the velocity is going up and down. All right, so not constant. Velocity is positive where the slope is positive. I just mentioned that. Negative where the slope is negative. And the velocity is 0 where the slope is flat. So in this particular graph, velocity is 0 at 6 seconds because we have a slope of 0, a flat horizontal line at 6 seconds. So before we do any problems based on position versus time graphs, I want to draw these 4 graphs. So you're going to have on your paper 2 graphs side by side and underneath that. So let's leave space to draw 4 graphs in that section. Okay, so we're going to have position on the y-axis and time on the x-axis. So let's say we have object A, and position on the is that line represents position. Let's say we have object B. Okay. In this case, because the line is straight, these A has a constant velocity. And it's going in the positive direction. B, also a constant velocity. And because the slope is positive, positive direction. Now, which one is moving faster? All right, it is B. B has a slope, greater slope, so B is faster than A, okay, because the slope is greater. Or steeper. In fact, I want to use the word steeper because when it's in the negative direction, that'll make more sense. Okay, now let's do another one. Got position, time, and let's go like this. So this will be A, and this will be object B. So A, once again, constant velocity because the line is straight. Negative direction, so it's moving left or down. B, also constant velocity, negative direction. Which one do you think is going faster? All right, I'll let you answer that. All right, the answer is B. because it's going in the negative direction, but it has a steeper slope. So the rate of change is greater. A slope is just a rate of change, and the rate of change is greater in B than A. Okay, let's draw a couple that have curves. Okay, so we have another position, time, and let's call this object A, and we'll call this object B. All right, so object A is going in the negative direction, and it's going slow to fast. It's getting faster. Now, why do I think it's getting faster? Well, here the slope is very shallow. But by the time you get over here to the right, the slope is very steep. So it's really moving faster as time goes on. Now, object B is in the positive direction. So these two objects are moving in different directions. But what do you think? Is B going slow to fast or fast to slow? All right, just like A, it's going slow to fast. Starts out with a shallow slope, but as time goes on, the slope is really steep over here to the right. So it's really cooking as time goes on. All right. This is our last one. Okay, let's call this A, and we'll call this B. Okay, A is which direction, positive or negative? All right, it's positive direction. Now, what do you think? Is it going fast to slow or slow to fast? All right, it's going fast because it's a steep slope, and over time it gets the slope gets shallower. So it's going fast to slow. All right, B, what direction is it? Positive or negative? It's the negative direction. What do you think? Is it going slow to fast or fast to slow? All right, just like A, it's going fast to slow. All right, very fast here because the slope is steep. Doesn't matter that it's negative. That just means it's going to the left or down. But here we're going boom. By the time we get here, we're really slowing down. All right, pause the video if you need to, and I'm going to erase or fast forward through all this. And we'll deal with working some problems with position versus time graphs. Okay, so we're going to do 1.4, 1.5, 1.6, and then I'll assign the homework from this section. Okay, 1.4, flip over to page 20. So you can see this is our graph, all right? And 1.4 says, is the object moving faster at 3.5 seconds or at 8.5 seconds? Well, I'm just going to leave the book here, and then you can write it on the answer on your notes. At 3, it's all about the slope when you're thinking about speed. So the slope at 3.5 seconds is really steep here. See, 3.5, really steep. The slope at 8.5 is less steep. Okay, so comparing the two, all right, here we are on page 20. 3.5 seconds is faster due to steeper slope. All right, let's look at 1.5. So 1.5 says, how many times does the object change directions? Well, the object changed directions every time that the slope changes signs. So the slope here is positive, 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 and then just past 4 seconds, the slope goes negative. So there's the first change in direction. And then at 8 seconds, it changes, the slope changes signs again. It goes from negative to positive. So that's the second, then the third, then the fourth at 10 seconds, fifth at 11, and then it doesn't change anymore. So we have 5 changes because we have the slope changes sign 5 times. All right, and then our last on your own of this lecture is, what is the instantaneous velocity at 1 second? So what we have to do is figure out the slope from this graph at 1 second. So we need an interval where the line is straight, not flat, not horizontal, just straight. And we're going to figure out the slope. That interval occurs between 0 and 2 seconds. That'd be a really good place to do it because you can read the graph well, okay? So let's calculate the slope. Where line is straight, not a bunch of bumps in it, and graph is easy to read. So that occurs between 0 and 2 seconds. So the slope is change in y over change in x. You might have learned in algebra class that that's y2 minus y1 over x2 minus x1. Okay, so read the graph. At 2 seconds, the position is 2 meters. At 0 seconds, the position is 0 meters. And then we have 2 seconds, that's x sub 2, minus 0 seconds. That's x sub 1. So that's going to be 1 meter per second. All right, so that does it for Lecture 1, Chapter 1. The homework is page 34. And make sure on this. Yeah, page 34. Review questions 1 through 5. And on page 35, practice problems 1 through 6. And I will make a video where we go over all of these. All right, so welcome to physics. I'm glad you could join us. That does it for Lecture 1.